This is the AIPMT 2015 question in thermodynamics. The question is like this. Figure below shows two paths that may be taken along a gas from A to C. So, if you see from A to C means it has been started here A, further it has gone to B and then to C. That's A to C. So, there are two paths. What are the two paths are? Let me write here. From A to C, we can go from A to B and then further B to C. That's one path. The another path is from A, we can go directly to C. This is the direct path. A to C, these are the two paths. Then in the process AB, that is in this process, you can see in the diagram, 500 heat is given, and the process BC, hundred joules of heat is added to the system. The heat absorbed by the system in the process AC will be how much? That's the question. So, according to first law of thermodynamics, the heat supplied to the system equal to change in internal energy and the external work done by it. You want the heat absorbed in the process AC. So, dQAC is dUAC and dWAC. dUAC is the change in internal energy in the process AC. dWAC is the work done during the process AC. First, let me calculate how do we measure dWAC during the process AC, how much work is done. Let's have a look at that first. So if you notice carefully, this is A, this is C. Work done in AC in a PV graph. The graph is a PV graph. So what we can say is, in PV graph, work done in a process is area under the PV graph. So if I have to calculate the work done during the AC, under this AC there is a PV, there is some area. I have to calculate the area of that graph. What is that area? This is that area. Right? This is the area under that graph. So if I have to find the area of that graph, if you notice carefully, there is a triangle. This is the triangle. And there is a rectangle. So area under that graph is area of triangle and area of rectangle. Let's calculate area under the triangle is how much. See, this is the triangle. Area under the triangle means formula is half into base into height. That's the area. So how much is the area of the triangle is half. Base means from here to here, where volume is changed from 2 into 10 power minus 3 to 4 into 10 power minus 3. So base is 4 into 10 power minus 3 minus 2 into 10 power minus 3. From here to here means difference between these two values has to be taken. And height means this is the height that are changed from 2 to 6. So height means 6 into 10 power 4 minus 2 into 10 power 4 in SI system. So how much is that? Let's calculate that. Half 4 minus 2 is 2 into 10 power minus 3. 6 minus 2 is 4 into 10 power 4. So that is half. 2 into 4 is 8. 10 power minus 3 and 10 power 4 is 10 power 1. That is 80 by 2. That is 40. So 40 joules, because we are calculating the work done. Area of the triangle is 40 joules. Similarly, I have to calculate the area of the rectangle. Area of the rectangle formula is base into height. This is the base. So area is base into height for a rectangle. Base is from here to here. That is 4 into 10 power minus 3 minus 2 into 10 power minus 3 meter cube. Height is from here to here. That's the height of the rectangle. That is 2 into 10 power 4 minus 0, started from 0. So this value is 4 minus 2 is 2 into 10 power minus 3 into 2 into 10 power 4. That is 2 into 2 is 4 into 10 power 1. That is 40 joules. So what we can understand basing on that is total area under AC equal to area of the triangle is 40 plus area of rectangle is 40, 80 joules. That is the work done. In the process, AC is 80 joules. So I have calculated this part already now as 80 joules. So if I have to solve the problem that is heat during the AC, I have to calculate the change in internal energy during the process AC. So my next task is calculating the change in AC. Once if you know that, you know the answer. So how do you calculate work done during, change in internal energy during AC? Let's have a discussion now. You can see from, as I have told, ABC is a cyclic process. A to C or ABC is a cyclic process. Initial and in both processes, initial and final states are same. As initial and final states are same, change in internal energy during the ABC is change in internal energy during the AC also. So, to calculate the change in internal energy during AC, I have to calculate the change in internal energy during ABC, where change in internal energy during the ABC can be written like change in internal energy during the AB, change in internal energy during the BC. So I have to calculate the internal energy during the AB case and BC case, add both of them. That becomes change in internal energy during ABC. That is the change in internal energy in AC because it's a cyclic process. So let's focus on that part of the problem, that is AB and BC, right? Let us see. During say state or process A to B, again I can write a formula dq equal to du plus dw. It is given that during AB 400 joules of heat is given to the system, so that is plus. During AB, what is internal energy that we don't know. Of AB plus what is the work done during the process AB is when you move from A to B this way, your volume is constant during AB. As volume is constant, work done equal to PdV. That is du of AB plus P, change in the volume equal to 0. That implies change in internal energy during the AB is the heat supplied itself, that is 400 joules. Now I got AB part, 400 joules. I need BC part. Let's talk about that BC part. During process BC, again I will use the same first law of thermodynamics, dq equal to du plus dw. It is given that during the process BC, 100 joules of heat is again given to the system. So that is plus 400. And du of that BC, I don't know. plus dW during the process BC, as the pressure is constant, dW can be written like PdV. Let's write that 100 equal to during internal energy BC PdV. Here the pressure is 6 into 10 power 4. dV during the process BC is, it has changed from here to here, that is 4 into 10 power minus 3 minus 2 into 10 power minus 3. That implies, 100 equal to change in internal energy during the BC plus 6 into 10 power 4. 4 minus 2 is 2 into 10 power minus 3. That is du of BC plus 6 into 2 is 12 into 10 power 4 minus 10 power minus 3 is 10 power 1, that is 120. That implies change in internal energy during the BC is 100 minus 120, that is minus 20 joules. Now I know change in internal energy during the BC minus 20, during the AB as plus 400. That implies what we can say is, total change in internal energy during the process AC is change in internal energy during the process ABC, because that's a cyclic process. That can be written as change in internal process during the AB and change in internal energy during the BC. During the AB, we found that value as 400 joules. During BC, that found it as minus 20. So this value is 380 joules. Now I know this value as 380 joules. As I know this and this, I can substitute in this formula and get our answer. It implies change in change in the heat supplied during the process AC is change in internal energy during the AC and the work done during the AC. Change in internal energy during the AC, we found it as 380, and work done in the process AC we have already calculated as 80. 380 and 80 is 460 joules, which is the answer for the problem, right? So it's a quite a lengthy problem, at least while I'm explaining. So I want you to follow carefully. The first thing is, whenever you look into the problem, the first thing is you have to see that what do you want to calculate. So you want to calculate the change in internal energy during the AC. So I have started from there itself. How can I calculate that? Using the first law of thermodynamics. To calculate the change in internal energy, to calculate the heat in AC, I need change in internal energy and I need work done. So first I have calculated work done during AC using simply the area under the PV graph. That is area of triangle and area of rectangle. I have calculated the area of triangle. I have calculated the area of rectangle and I have added both of them. So I got the work done during AC. Next thing is to calculate the change in internal energy during AC. As it is a cyclic process, change in internal energy during ABC equal to the change in internal energy during AC. Change in internal energy in ABC is the sum of internal energy along AB as well as BC. So I have calculated change in internal energy during AB, again using the first law of thermodynamics in the process AB. Again, similarly, I have calculated the change in internal energy in BC in the process BC, again using the first law of thermodynamics. So though it is lengthy, I have simply followed basic laws of thermodynamics itself. By adding both of them, I have calculated the total internal energy as I have shown here. I have substituted both these values in this place and got my answer. I want you to re-look into this problem once again carefully, and if you have still anything to ask, you can just put a comment here in the video. That's it, and thank you for watching.